Imagine holding the future of computing, maybe communication, even augmented reality. Not as some far-off sci-fi idea, but right here on a tiny silicon chip.
Right. Tangible tech.
And what if that chip could bend light to its will, not just in the ways we're kind of used to, but across colors and conditions that were basically impossible before on a chip?
We're talking visible light, even UV, yeah. Stuff silicon photonics just couldn't handle.
Exactly. Think about, the speed of your internet, the potential for VR headsets that don't feel like bricks on your face. It's all powered by photons, these little packets of light doing amazing work behind the scenes.
The unsung heroes, definitely.
So today we're doing a deep dive into something really groundbreaking. It's about extending what we can do with light on chips, pushing into those shorter wavelengths we just mentioned. Our mission here is to unpack how this new tech could, well, pretty much revolutionize everything from quantum computers to the gadgets you might be wearing tomorrow.
And we're looking at a specific paper for this, right?
We are. It's titled Extending the Spectrum of Fully Integrated Photonics to Submicrometer Wavelengths. And it's published in Nature, which is a big deal.
Absolutely.
The work comes from a large team, Min A. Tran, Chong Zhang, Theodore J. Morin, and many others, Lin Chang, Sabyasachi Barak, folks from Nexus Photonics, UC Santa Barbara, Caltech, a real powerhouse group.
Top researchers in the field.
And don't worry, we'll guide you through it. We want to pull out the really cool stuff without getting bogged down in, overly technical jargon.
Sounds good. So maybe we should quickly set the stage. Integrated photonics.
Yeah.
What is it, basically?
Good idea.
Well, think of it like this. You know how microchips cram millions of electronic components onto a tiny piece of silicon?
Right, for computers and phones.
Integrated photonics aims to do the same thing, but for light. Cramming entire optical systems, lasers, detectors, waveguides, the whole lot onto a single chip.
Okay, so microchips for light and the benefits.
Oh, they're huge. You get incredible scalability, meaning you can make tons of them cheaply, they're way lighter, cost less, and use much, much less power than traditional bulky optical setups.
Got it. Makes sense. And for a while, the star player in this field was Silicon Photonics, or SIF.
That's right. SIF was, and still is, a massive step forward. It cleverly piggybacked on the huge manufacturing processes already in place for electronics.
Using the same silicon factories.
Exactly, which made it fantastic for things like speeding up data centers, building optical links for AI chips, enabling LiDAR for self-driving cars. Tons of applications.
But there's always a but, isn't there?
Usually. In this case, yes. SIF ran into a fundamental problem. We sometimes call it the silicon wall.
The silicon wall. Okay, what's that?
Well, silicon itself, the material, it has this property, it's band gap. That means it absorbs light very strongly at wavelengths shorter than about 1.1 micrometers.
So anything shorter than near infrared, basically. Visible light, UV.
Exactly. Silicon just soaks it up. It can't guide it or manipulate it efficiently. So all those applications needing visible light, or even certain near-infrared or UV wavelengths, they were stuck. Silicon photonics couldn't really help them on chip.
It's like having this amazing toolkit, but it only works in the dark, metaphorically speaking.
Sort of, yeah. It locked out a whole range of possibilities that need those shorter wavelengths.
Okay, so if silicon hits a wall, what's the alternative? You mentioned this Nature paper found a way around it.
Right, so people knew about other materials. One really promising one, especially for the passive parts of the light pipes or waveguides, was silicon nitride, SiN.
Silicon nitride, what's good about it?
Its biggest advantage is incredibly low light loss. Light can travel through silicon waveguides without getting absorbed or scattered much. And crucially, this holds true even way down into the visible spectrum, like below 460 nanometers blue light.
Wow, okay, so it solves the absorption problem silicon had.
It does for guiding light. Plus, it's actually cheaper to make SiN layers on silicon wafers than the specialized silicon on insulator, or SOI wafers used for standard SIF.
Cheaper and works for visible light. Sounds perfect. What was the catch?
The catch was integrating the active components. The things that actually make light, like lasers or amplifiers.
Ah, right. You need those too.
Definitely. And those active parts are typically made from different materials called 3V semiconductors. Think gallium arsenide, indium phosphide.
Okay.
The problem was 3 materials and silicon nitride have very different optical properties, specifically their refractive index. Trying to get light to jump efficiently from a 3V laser into a SiN waveguide was, well, it was really inefficient. Like trying to connect a garden hose to a fire hydrant, the connection's just not right.
You lose most of the light at the connection.
You got it. Huge losses. And that integration challenge is what Min Tran and the team really tackled head-on.
So this is the core of their breakthrough in the Nature paper, figuring out that connection.
Precisely. They developed what they call a heterogeneously integrated ThRVS platform. Fancy name, but the idea is clever.
Break it down for us.
Okay, so they take these specialized 3V lasers, the ones that can make light, and they bond them directly onto the SIN waveguides, which are already sitting on a standard silicon wafer.
Bonding different materials together on a chip, that sounds delicate.
It is, but they figured out a scalable way to do it. But the real magic is how they handle that refractive index mismatch, the connection problem. Instead of forcing a direct connection.
They built a bridge.
Exactly. They designed a special intermediary waveguide structure. Think of it as an adapter. It efficiently guides the light from the third material into the SIN waveguide.
And it worked?
It worked really well. They got coupling efficiencies up to 70% in their first try.
70%? That's pretty good, right?
It's excellent for a first generation, and they predict they can push it over 90% with refinements.
Yeah.
And maybe the biggest wow here is the scalability. They demonstrated this on a full 4-inch wafer. Not just one or two devices, but hundreds of working lasers fabricated across the wafer using processes compatible with high-volume manufacturing.
Okay, that is big. It's not just a lab curiosity, it's a path to actually making these things.
That's the key. It's manufacturable.
So they solved the integration. What could they actually build on this new platform? What tools are now in the photonic toolkit at these shorter wavelengths, like the 980 nanometers they focused on?
Well, they basically demonstrated all the essential building blocks you'd need for complex optical circuits.
Like what?
Okay, first, lasers. They made Fabry-Perot lasers that turned on with low current, just 12 milliamps, and put out good power, over 25 milliwatts, efficient and powerful.
Nice. What else?
Amplifiers. Semiconductor optical amplifiers, SOAs, that could boost the light signal by over 22 decibels. That's a lot of gain.
Crucial for sending signals over longer distances on the chip, right?
Absolutely. Then, photodetectors, the eyes of the chip. Their photodiodes were very sensitive, high responsivity, and had extremely low dark current, meaning they don't generate much noise when there's no light.
Good for detecting faint signal.
Exactly. And modulators. They built Mach-Sender modulators, which are key for encoding data onto light beams, and got high extinction ratios, meaning a clear on and off signal.
So lasers, amplifiers, detectors, modulators. Sounds like a complete set.
Pretty much. And all connected by those super low-loss SIN waveguides, remember? Losing less than half a decibel per centimeter of travel. It's a full system on a chip, now working below that old silicon limit.
That's impressive in itself, but I hear the performance of some of these components, especially the lasers, was where things got really exciting. Talk about coherence.
Yes. Coherence. For a laser, that basically means how pure the color is or how stable the light wave is. Think of it like a musical note. A coherent laser is like a perfectly pure tone, no wavering, no static.
Why is that important?
It's incredibly important for anything requiring high precision. And the lasers they built on this platform were astonishingly coherent.
How good are we talking?
They measured a Lorentzian line width, that's the technical term for this, purity of just 2.8 kilohertz for one laser. Typical values were around 10 kilohertz.
Okay. Is that good?
It's amazing for an integrated laser on a chip. Previous integrated lasers, especially 3V ones, were often over 100 kilohertz, sometimes much more. Getting down to the single-digit kilohertz range is a massive leap.
Right. And what does that narrow line width enable?
It lets you interact very precisely with things that are extremely sensitive to specific frequencies of light, like atomic transitions.
Like for atomic clocks or quantum computing.
Exactly. Those applications need lasers with extremely pure frequencies to talk to individual atoms or ions without disturbing neighboring ones. This narrow line width is a game changer for putting those kinds of quantum and atomic systems onto chips.
Wow. So super precise. What about flexibility? Could they tune the laser's color or frequency?
Oh yeah, that was another big highlight. Super tunability. The lasers offered a wide tuning range, about 20 nanometers around that 980 millimeter center wavelength.
20 nanometers. How much is that in frequency terms?
That translates to roughly 6 terahertz. That's a huge spectral window you can scan across.
Terahertz. Okay, that sounds like a lot.
It is. It means you can dial in the exact frequency needed to hit a specific atomic resonance, for instance. They even showed off this control by basically drawing the letters UCSB by stepping the laser frequency very precisely point by point.
Huh. That's a cool demo.
But maybe even more important than the total range was how it tuned. They achieved mode hop-free tuning over more than 8 gigahertz.
Mode hop free, what does that mean?
You know how sometimes a radio station might suddenly jump or get static as you tune. A mode hop is kind of like that for a laser, an abrupt jump in frequency. Mode hop free means you can smoothly sweep the frequency without any of those sudden disruptive jumps.
Okay, and why is that critical?
It's vital if you need to lock the laser's frequency to a very precise reference, like an atomic transition for a clock. You need that smooth, continuous tuning to stay locked on target. No jumps allowed.
Precision, tunability.
Yeah.
Anything else that stood out?
Yes. One more absolutely huge factor, especially for practical applications. High temperature operation.
Right, you mentioned heat can be a killer for electronics and photonics.
It really can be. Most complex photonic chips need active cooling, like little refrigerators, which use power and add complexity.
So how did these new lasers fare?
Amazingly well, because these shorter wavelength IV materials inherently handle heat better, something about their band gaps and keeping electrons contained.
Okay.
The team demonstrated their lasers operating continuously, pumping out light at up to 185 degrees Celsius.
185 C, that's boiling point is 100 C. That's incredibly hot.
It is. It completely blows away the previous record for integrated lasers on silicon, which was around 150 C.
What does that mean in practice? Why is operating at such high temps so important?
It means potentially getting rid of the need for cooling in many situations. Think about data centers, huge energy costs just for cooling. If the chips themselves can run hot, you save enormous amounts of energy.
Greener data centers.
Yes. And it also means these chips could work in really harsh environments, maybe sensors inside engines, or probes in hot industrial processes, or even space applications without needing bulky, power-hungry cooling systems. It just makes the technology way more robust and versatile.
Okay, let's tie this all together. We've got this new platform. It breaks the silicon wall, enables visible light on chips, gives us lasers that are super precise, tunable, and run incredibly hot. What does this mean for, us, for the technology we might actually use?
Right, the so what factor.
Yeah.
Let's start with AR and VR, augmented and virtual reality.
Yeah, the headsets are still pretty bulky.
Exactly. This platform could be key. Imagine combining these efficient visible light sources with on-chip beam steering optical phased arrays all integrated together. You could potentially shrink down the projection systems dramatically.
Making headsets lighter, smaller, less power hungry.
That's the dream, more like wearing a regular pair of glasses. This tech gets us closer.
Okay, AR, VR. What else? You mentioned data centers.
Yeah, the energy savings from reduced cooling could be massive, just making the internet's backbone greener. Plus, it opens doors for actual photonic computing using light for processing, which could be way faster for certain tasks.
And the really high-tech stuff, atomic physics, quantum.
Huge implications there. On-chip, atomic clocks, way more portable and potentially even more precise. Next-gen quantum computers using trapped ions controlled by these integrated lasers. Advanced sensors for measuring things with incredible accuracy.
Like better GPS, maybe, or tools for scientific discovery.
All of the above. And don't forget biosensing and imaging. Being able to integrate visible light sources and sensors on a chip opens up all sorts of new possibilities for tiny medical diagnostic tools or environmental monitors.
It sounds like it touches almost every area of advanced tech.
It really has that potential because light is so fundamental.
And you mentioned earlier, it's potentially cheaper and scalable.
That's crucial. The fact that it uses silicon nitride, which is cheaper than standard SOI wafers, and that the bonding process is designed for high-volume manufacturing. That's key.
So it's not just better, it could actually bring costs down.
That's the hope. It makes advanced photonics more accessible, not just locked away in high-end labs. It could genuinely democratize this kind of technology.
Okay, let's try to boil this down. If someone takes away just a few things from our chat about this Nature paper, what should they be?
All right. Takeaway 1. We've broken through the silicon wall. This new 3V on silicon nitride approach lets us manipulate visible and UV light directly on a chip, which silicon alone couldn't do. Big expansion of capability.
Got it. Break the wall. What's 2?
Takeaway 2. Unprecedented performance, especially the lasers, incredibly precise frequencies, narrow line widths, wide tunability, vital for quantum tech, atomic clocks, and advanced sensing.
Precision and control. Okay, number 3.
Takeaway 3. Runs hot, stays cool. The ability to operate at record high temperatures, like 185 Celsius, means huge potential energy savings, particularly for data centers, and makes devices much more robust for harsh environments. No need for bulky cooling.
Right. Break the wall, precision control, and runs hot. That covers a lot.
I think so. It really shows how smart engineering can overcome what seem like fundamental limits in materials.
It really is a testament to rethinking the building blocks, isn't it? How combining these different materials in a clever way unlocks so much potential.
Exactly. It could quietly change so many things, from the way we experience virtual worlds to how we literally measure time.
So the final question for you, our listener, to think about. As this kind of integrated photonics gets smaller, cheaper, and works across more colors, even in tough conditions, how do you see your interaction with light-powered tech changing in, say, the next 10 years?
Yeah, what happens when the chips inside your devices can suddenly see and use the full spectrum of light?
Will your next phone have advanced medical sensors built in? Will AR finally feel seamless? Something to ponder. We'll leave it there for this deep dive.